Hi YouTube, Profilo is continuing the series of video about the problem on the wood chipping machine FARMI Profi CH27. This video is about the reverse engineering process, so all the actions that led me to understand how the whole system works and the fact that I choose the Arduino Uno in order to solve this problem. First of all, we have to understand which are the functionalities that we want on the machine. The first main feature are the forward and the backward direction for the feeding crane. In order to do that, we need two digital inputs that are those coming from the yellow control and yellow box here. This is the radio control. You have two arrows and you command the forward and the backward direction. Inside the yellow box here, there is a specific board that controls two relays, and these two relays are closing two small circuits, one for the backward direction and the other for the forward direction. So this is perfectly suitable for the Arduino Uno since it is able to read two digital inputs. We have then two digital outputs down there for the electrovalves. One is commanding the oil inside the hydraulic motor for the forward direction, and the other electrovalve is commanding the oil for the backward direction. These are two digital outputs that I'm going to command with two digital outputs of the Arduino, and also this application is perfectly suitable. So with two digital inputs and two digital outputs, you are able to perfectly restore the original and the manual functionalities of the machine. So we can do that with the Arduino. Since I also have a speed sensor back there, I was also wondering if I was able to do like a no stress feature, the one that the original computer implements. In order to do that, first of all, I had to understand how is the signal coming from the sensor made, and second, if the Arduino is fast enough to see the rotation, to measure the rotation speed. This sensor, the speed sensor, is an inductor sensor, meaning that on the rotor there is a small slice of metal, and when this slice of metal passes in front of the inductor sensor, then the inductor sensor, since it is an active low sensor, returns 0 volt. When the sensor is not seeing anything, so meaning that the rotor is going forward, is rotating, it actually returns a 12 volt signal. This means that we do have a square wave, 0 volt when you're reading and 12 volts when you're not reading anything. And you have this square wave that is generated while the rotor is moving. In order to better understand how this signal is made, I have connected an oscilloscope to the machine in order to find out which are the times, the reading times and the non-reading times, and which are the distances between two rising or falling edges of the signal in order to actually compute which is the rotation speed. Let's then analyze the signal coming from the oscilloscope. The first signal, the yellow one, is the one coming from the inductive sensor that measures the rotation speed of the rotor. It's an active low sensor, so we have 12 volt when reading and 0 volt when reading. And these falling edges are the moments in which the inductive sensor actually reads the metal plate onto the wood chipper rotor. So every time you see a falling edges, this means that the wood chipper rotor has performed a complete turn. So in order to compute the rotation speed, I actually wanted to measure the time distance between two falling edges. Let's call this like a period of time t. I'm going to show you which is the formula I used. The RPM, revolute per minute formula, is something like that. You are doing one revolute in a certain amount of time t. This time t is in actually milliseconds, so I want to convert it in seconds by dividing the time for 1000. And finally, you have to remember that you have 60 seconds in 1 minute, right? And so you're going to complete the formula with this conversion here. When we were doing some experiments with the oscilloscope, the machine was running at 1000 RPM. The time that we measured was in fact of almost 60 milliseconds. And if you do some calculations, in fact, you're going to have 60 milliseconds divided by 1000, finally times 60, you are able to find out that you have in fact 1000 RPM as rotation speed. So this is the right formula that I was using. Another very important feature of this signal is the time duration of this interval here, that is the reading time of the inductive sensor. This is really important because that duration, and we have seen with the oscilloscope that still at 1000 RPM, we are at about 1.89 milliseconds of time duration. This is really important for us because it gives us the idea on how much fast needs to be the Arduino in order to sample the signal. You are able to see, in fact, in the oscilloscope, another signal, another blue signal, that is a signal coming from the Arduino. In particular, it is a square wave down like that, and it is a 5 volt to 0 volt square wave because I have connected one digital output pin to the oscilloscope, and after the void loop, at the end of the void loop, I've inserted a digital write function that at the end of every cycle toggles a variable that actually toggles the voltage on a digital output. So I am able to understand which is the time duration of a single void loop cycle of the Arduino. With the oscilloscope, we found out that that time duration of the Arduino is about 930 microseconds. And remember that here we have that the reading duration is about almost 1.9, let's say, milliseconds. So if we want to zoom in, it means that if the time duration of the signal, we have that the square wave of the Arduino is sampling at least 2 times the square wave coming from the signal, in particular in the reading phase. So we are perfectly able to understand when there is a falling edge or not. In the information theory, there is an important theorem about the signals that stands like this. If you do have a signal that has a specific frequency, in order to properly sample it, you need to double the frequency, and this calculation is actually the sampling frequency. So sampling frequency. This is the theorem. So we have to check if this is satisfied in our case. The sampling frequency in our case is the signal coming from the Arduino. So the frequency of the Arduino is actually 1 over the period of the calculation. So we have 1 over 930 microseconds. And at the end of all, we have that the frequency is about 1075 Hertz of frequency. The signal frequency is actually a bit different. That's true that the period of time is a long period here, as I told you, is about 1.9 milliseconds, but actually the signal that we want to be able to recognize is this small reading interval here. So the period of the signal is a smaller time. So we have that the frequency of the signal is 1 over this period, that is 1 over 1.9 milliseconds. And doing them calculation, you're gonna have that this is about 530 Hertz. So we're gonna check if the Shannon theorem is actually satisfied by comparing the two frequencies. The sampling frequency is 1075 Hertz over 530 Hertz coming from the real signal. By doing this calculation, you see that we have 2.02 pure number. So yeah, we do not have that much margin, but actually we can work. Remember that 1000 RPM is the maximum speed of, in our case, of the wood chipper. Actually, we want to work to 907 RPM, so this is going to be easier. We have a bit more margin, and moreover, remember that you can always try to write a more efficient code with respect to mine. After this analysis with the oscilloscope, we found out that we were able, with the timing and also with the frequency, with the computer frequency of the Arduino, we were able to measure the speed. And so we decided to go forward and we opened this black box here, we found out which is the cable of the signal, and then we connected it to an analog input of the Arduino. To do that, since this is like an automotive application, meaning that we are running at 12 volts, I had to build, you will see that specifically in details in the hardware video, let's say, we had to build a voltage divider in order to bring the tension from 12 volts to 5 volts, and then we have connected this 5 volt square wave signal to an analog input of the Arduino in order to measure the tension level and then find out the folding and rising edges in order to measure the speed of rotation of the system. The no stress that have been implemented is the same already present in the original FARMI controller, meaning that if the rotation speed goes below a certain threshold, then the feeding of the material is interrupted, and moreover you are commanding a backward direction a bit in order to detach the wood from the knives. The rotation speed has to restore to the original value so that you are not mechanically loading the tractor behind me, and then when you're ready again you can proceed with the normal work, so typically forward, and then if you want you can command backward or forward. It depends on what you have to do. This is the reverse engineering process. I have a 12 volt power supply coming from the tractor, and inside this box you will show the other part, that is the circuitry and the implementation with the Arduino, with the relays and the voltage divider. I'm going to show this in the next video.